Today we are going to consider the chapter of refraction of light. When we talk about light, certain concepts that we have studied about light in the 9th standard or the 8th standard. Let's take a brief recap of it. When we take a recap of it, we should know what exactly is light. How does light constitute? What are the ingredients of light? How is light formed? Light is nothing but an electromagnetic wave which is formed by the combined effect of electric and magnetic fields that are held mutually perpendicular to each other. So if we plot a graph of displacement versus time, we see that the electric wave takes up the x-axis, the magnetic wave takes up the y-axis, and it is the third wave that is mutually perpendicular to electric and magnetic waves that constitute the electromagnetic wave. It is transverse in nature. At the same time, it travels with the speed of 3 into 10 to the power 8 meter per second. During 9th standard, we studied about reflection of light also. Here we are studying a different phenomena, that is refraction of light. How do we define refraction of light? Refraction of light is nothing but the deviation of path of a ray that is traveling from one optical medium to another. So, when a ray of light is incident on an interface is nothing but a surface or a boundary that separates two optical media. So, when a ray of light travels from one optical media into another, we see that it changes its path. This change in path or this deviation in its original path is called as refraction. Why does it occur? It occurs purely on account of difference in optical densities, difference in the refractive indices of the two medium. So when we talk about refractive index or the refractive index of a medium, we say that refractive index is nothing but the ratio of sine of angle of incidence to sine of angle of refraction. To consider this in more details, let's consider an optical glass slab. When a ray of light is incident from air to glass, that means it is traveling from an optical rarer medium to an optically denser medium. By the principle of refraction, we see that the ray of light would bend towards the normal. So when a ray of light travels from a rarer medium to a denser medium, it bends towards the normal. However, when a ray of light travels from a denser medium to a rarer medium, it bends away from the normal. When a ray of light travels from a denser medium to a rarer medium, it bends away from the normal. So when the same light travels from water to air, that means traveling from denser to rarer, we see that it bends away from the normal. These two principles, when applied to our day-to-day examples, we study different types of refraction that occur. While considering the chapter on refraction of light, we study a lot of day-to-day examples as rising of sun, setting of sun, star twinkling, the pond appearing to be raised or the coin appearing to be raised when dipped into water, the stick appearing to bend, and so on and so forth. So we see that at every juncture of our life or every part of our life, we do apply the principle of refraction. When we consider refraction of light, we definitely know that we have to have a base background of what we studied in our previous years. We should know what is light. Light is nothing but an electromagnetic wave which is formed by the combined effect of electric and magnetic waves which are held mutually perpendicular to each other. So if I have the x-axis and y-axis, I see that the electric wave travels across the x-axis the magnetic wave travels along the y-axis. It is the third axis, that is the z-axis, that constitutes the electromagnetic wave. This wave is perpendicular to both electric and magnetic field and is a result of varying electric and magnetic fields. So when two mutually perpendicular varying electric and magnetic fields are held together, we get the combined effect of these two fields as the electromagnetic wave. This electromagnetic wave travels at the speed of 3 into 10 to the power 8 meter per second. At the same time, it does not require a material medium to propagate. Let's consider refraction of light. What do we know about refraction? Let's consider our interface. An interface is nothing but it's a boundary, that surface that separates two optical media. So that means we are talking about a rarer medium and a denser medium. When a ray of light travels from an optically rarer medium to an optically denser medium, it bends towards the normal. Or the other way around, when a ray of light travels from a denser medium to a rarer medium, it bends away from the normal. This bend in path or this shift in path of the light ray is called as refraction. This occurs purely on account of difference in optical densities. However, it also defines the refractive index of the second medium with respect to first. While considering this, we have one basic concept, what is known as lateral displacement. In order to understand lateral displacement, let's consider an optical glass slab. An optical glass slab in which a ray is incident on the first phase, say phase AB. That means it is traveling from a rarer medium to a denser medium, while it is traveling from air to glass. When a ray of light travels from rarer to a denser medium, we see that it bends towards the normal. So there is going to be a shift in path of the original incident ray after suffering refraction. This particular ray, as it travels through the glass, it being a homogeneous medium, will continue the same path till it strikes the second interface, say CD. Now at this interface, it is going to travel from a denser medium to a rarer medium, that is from glass to air. As it travels from denser medium to a rarer medium, it bends away from the normal. But then that emergent ray is basically parallel to the original incident ray. So if I produce the incident ray in such a way that the optical glass was not present, then I see that the emergent ray and the extended incident ray are parallel to each other. There is a perpendicular shift between the original incident ray produced and the emergent ray. So that perpendicular shift is called as lateral displacement. So we define lateral displacement as the perpendicular shift between the original incident ray produced and the emergent ray after suffering refraction through an optical glass slab is called as lateral displacement. When we know the study of lateral displacement, we have factors on which lateral displacement depends. Lateral displacement definitely depends on the thickness of the glass slab. Thicker the glass slab, more is the lateral displacement. It also is dependent on angle of incidence. It also is dependent on the refractive index of the second medium. So we see that these factors affect lateral displacement. There is one major law in case of refraction of light that we ought to know. It was designed by a scientist called Snell. Snell's law states, for a given pair of optical media, the ratio of sine of angle of incidence to sine of angle of refraction bears a constant ratio. Ratio of sine of angle of incidence to sine of angle of refraction bears a constant ratio. This ratio is called as the refractive index of second medium with respect to first. This ratio is called as the refractive index of the second medium with respect to first. Why second medium with respect to first? Purely because it is after entering the second medium, the ray is being deviated. So we are talking in terms of the second medium with respect to first. How much is the ray deviated from its original path? That is how Snell put it across. Based on this law, we have a mathematical relation, that is refractive index of second medium with respect to first is equal to sine I upon sine R. Sine I upon sine R. However, if the ray is incident normally to the surface, we see that this ray of light would travel undeviated. That means angle of incidence is equal to angle of refraction. We have a concept what is known as concept of real depth and apparent depth. A very interesting phenomena. We have so many applications also based on this. Just to give you a typical example, I consider a beaker or a glass trough that is filled with water. What I do is that I drop a coin into it. As soon as I drop a coin into it, I see that apparently the position of the coin is seen to be raised. Why does that occur? Simple logic. If we consider any point on the coin, the apparent image of the coin, we take two rays that are originating from this particular apparent image. We see that the ray of light is striking the interface of water and air. As soon as the ray of light travels from a denser medium to a rarer medium, that is water to air, what is going to happen? It would go away from the normal. So when a ray of light travels from a denser medium to a rarer medium, it bends away from the normal. As soon as it bends away from the normal, we trace these paths backward to get an apparent image. We see that this apparent image is virtually raised, which gives you the apparent depth of the object. So we have the apparent depth and we have the real depth of the object. Definitely we can also define the refractive index in terms of real depth upon apparent depth. Another example to give you for real depth and apparent depth. Say for example, I have a glass containing water. I dip a pencil in it. See how peculiar phenomena this is and how interesting it is. When I just start dipping the pencil into it, I see that at the interface, the stick appears to be raised as if somebody is pushing it from below and bending the stick. This phenomena of bending of stick is also because of refraction of light. Are you seeing this stick that is being bent? There is a stick that is straight enough, which we are putting inside, or a pencil that we are putting inside. At the interface, we see that it is being lifted or raised. That means there is an apparent image of the pencil that is being seen. This apparent image is again because of the concept of refraction of light. A ray of light from the tip of the pencil is moving from a denser medium to a rarer medium, as a result bending away from the normal, tracing the rays backwards, we get an apparent image of the pencil. Why do stars twinkle? Another application based question. We are on the Earth's surface. definitely we see that there are a large number of layers across the atmosphere of the Earth with different optical densities. Why the optical densities are different? Because the air layer that is near the Earth's surface is the hottest. That means the volume is more, density is less. As we go away from the Earth's surface, density keeps on increasing. So optical density maximum, optical density minimum. When it is traveling from a denser medium to a rarer medium, it goes away from the normal. And when we trace these rays backwards, we see that we get an apparent image of the star. But since the distance between the Earth and the star, that is a luminous body, is so large that we see as if the star appears to twinkle. This again is a very good example for real depth and apparent depth, or the concept of refraction of light. So we see that there are so many examples on day-to-day basis which explains the concept of real depth and apparent depth. It plays a very vital role in our day-to-day life. Let's go on to the next concept, that is critical angle and total internal reflection. Talking about critical angle, let's consider again a glass trough that is filled with water. I have a light source over here at the bottom of the trough. Let's consider various rays, ray 1, 2, 3, 4 and so on as shown in the figure. The first ray of light is traveling from water to air, so traveling from denser medium to a rarer medium. A ray of light passing from denser medium to a rarer medium bends away from the normal. I keep on changing the angle of incidence. Slowly and steadily I go to ray 2. I see that it still bends further. I go to ray 3. It still bends further. Till I reach the ray 4, where I see that this ray of light, after suffering refraction, is scraping through the surface. That means the angle of refraction is 90. So I define critical angle in this case as that angle of incidence, that is with the ray 4, for which the corresponding angle of refraction in the denser medium is 90 degrees, is called as critical angle. That angle of incidence for which the corresponding angle of refraction in the denser medium is 90 is called as critical angle. Again, this angle is very important. What is the physical significance of this? Let's continue drawing the fifth ray. What should be your assumption? After suffering refraction, we see that it has bent through various angles, come up to the surface. Now, if I draw the ray 5, where should the ray go after suffering refraction? Yes, in this case, we see that instead of refracting, it is reflecting back into the same medium. This phenomena is called as total internal reflection. So, for an angle of incidence that is greater than the critical angle, we see the phenomena of total internal reflection. So, we define total internal reflection as when a ray of light travels from a denser medium to a rarer medium at an angle of incidence greater than critical angle, it reflects back into the same denser medium, obeying the laws of reflection. This particular phenomena is called as total internal reflection. This phenomena also is very important. As I said, we have a large number of applications also on this. Just to enlist a few, if the same glass trough, I just lift it across so that it is above your eye level. What do we see for the lower meniscus of water? We see the lower meniscus of water to appear to be silvery. Is it that water is silvery? No, water is transparent. But because the ray of light is striking that surface at an angle greater than critical angle, we see that it reflects back into the same medium, thereby appearing it to be silvery. Second example over here that we can quote very easily is diamonds appearing to sparkle even in the dark. You all must be crazy about diamonds, right? In diamond, we see that the edges or the surfaces are cut across, so that when light is incident in a diamond, we see that it strikes the surface at an angle very small enough so that that light that is striking the diamond surface starts reflecting. The critical angle for diamond is just 24 degrees. So any angle that is greater than 24 will start suffering total internal reflection. So I see that once the ray of light is struck the diamond crystal, it starts reflecting across various surfaces. As a result, light is entrapped into the surface. When the light is being entrapped, if I take this diamond into a dark room, what is going to happen? The light that is entrapped inside will make the diamond glow or sparkle. That is why we say that diamond, even when taken in the dark, appears to glow or sparkle. We have the concept of mirage also. If you have been to deserts, say in Arabic countries, we see that this particular concept of mirage is seen. The people in the Arabic countries definitely have large amount of water storage that is required while they travel from one place to another. How do they do it? Or how do they locate the position of a pond? It is because of the apparent image of a plantation that they see across the sand surface. So wherever there is a water body, we see that there is certain amount of plantation over there. Say something like date palm trees or coconut trees or whatever. Now when this date palm tree is seen as a virtual image, as an image that is obtained because of ray of light that is traveling from various optical densities at a particular angle of incidence, we see that this ray of light, rather than further refracting, it starts reflecting. The moment it starts reflecting, it reaches the eye of the Arab traveler, and hence if they extend all these reflected rays backwards, we see that this Arab definitely locates the position of the oasis. This oasis can very easily be detected by the means of total internal reflection. So there are a large number of day-to-day examples as far as total internal reflection also is concerned. In order to understand total internal reflection, we have to consider isosceles right angle prisms in which both the angles of the triangle are 45 and it has a 90-degree angle in it too. So let's consider an isosceles right angle prism and a ray of light that is incident on it, normal to the surface. So when a ray of light is incident normal to a surface, we see that this ray of light would go undeviated. It strikes the hypotenuse. At the point of incidence, we draw a normal. We calculate the angle of incidence which this refracted ray has made with the normal. We calculate it by the geometry of figure. We know that one of the angle is 90. This angle is 45. This is perpendicular to the base. At the same time, the ray is perpendicular to the incident surface. That means the base is parallel to the refracted ray. If we draw transversal, we get the corresponding angle also as 45. So when the corresponding angle is 45, we see that the angle of incidence also works out to be 45. This is because the normal makes an angle of 90 degrees with the refracting surface. So at an angle of 45, we see that the refracted ray strikes the hypotenuse. The critical angle for a glass prism is given as 42 degrees. What do? We compare the critical angle with the angle of incidence. Since the angle of incidence here is greater than the critical angle, we say that TIR occurs. That is, total internal reflection occurs. This total internal reflection is going to reflect the ray back and strike the base now, obeying the laws of reflection. That means angle of incidence equal to angle of reflection. The reflected ray will strike the base at an angle of 90, that is again normal to the base, and hence go undeviated outside. So if I consider an object, say having a head and a tail, or if I consider a person that is standing over here, and if I try to locate two rays that are passing from his head as well as his toe, and we try to trace the same path, we see that the person is being rotated through 90 degrees. So if I have to rotate the image through 90 degrees, I can very easily use the concept of total internal reflecting prisms, of course with an isosceles construction. If I have to rotate the same thing against around 180 degrees, I shift the object parallel to the hypotenuse. When I shift the object parallel to the hypotenuse, I see that two rays that are coming across perpendicular to the hypotenuse strike the vertical surface. So they are going undeviated through the hypotenuse and striking the vertical surface. Again, at the point of intersection or incidence, I draw the normal. When I construct the normal by the geometry of figure, I find that the angle of incidence in both the cases is 45, definitely greater than 42. Since it is greater than 42, it will obey the laws of reflection and perform total internal reflection. So on reflecting back, it strikes the base at an angle of incidence again equal to 45 by the geometry of figure. When it strikes the base at 45, again would suffer total internal reflection and get reflected back normal to the hypotenuse. So in this case, we see that the object is being rotated through 180 degrees. That is, the head has become the toe and the toe has become the head. So we can use basically these total internal reflecting prisms to rotate the object through 90 degrees or rotate the object through 180 degrees. In case of total internal reflecting prisms, we see that very small amount of energy is being absorbed. So the advantage of total internal reflecting prisms is that it absorbs minimum amount of energy as compared to even a plane mirror. So we can use it for reflection without consumption of any energy or without dissipation of any energy.